This conference will now be recorded.
Hello everyone. So today's topics will start with problem, but this problem is based on redox titration. Redox reactions as the basis of titration. So that topic we have started in the last class, and under that topic we have total 3 types of titration. The first is already we have covered, and that is permanganate titration. And this problem that you are seeing now, that is based on permanganate titration. And the next one is Dichromate titration, and the third one is Iodimetric and Iodometric titration. So the rest of the two we will cover today. And first one is already covered, and this problem is based on the first titration, which is Dichromate titration. So here the problem, it looks very that is big problem, but actually it will not take much time. Fine. And there are total 2 answers that we have to give. So it is saying that a sample, the mass of the sample is given, which is 5.6 gram, and in that sample there is presence of iron. This iron is completely dissolved in cold dilute HCl, and a solution of 250 ml that is prepared. Now out of this 250 ml solution, only 25 ml is taken, and this 25 ml of the solution that is just prepared, it requires this ml of and 0.03 molar of permanganate solution to reach the end point. That means for titration, this amount of KMnO4 is required for 25 ml of the solution for the to end the process. That is, end point means now all the Fe2 plus that is consumed by MnO4 minus. Now the question is number of moles of iron 2 plus present in this 250 ml solution that you have to express in this format, x into 10 to the power minus 2. So you have to find the value of x, and you also have to consider complete dissolution of FeCl2. So in this solution that we have prepared in acidic medium, obviously you will see that mostly KMnO4 reaction, it is always in acidic medium, that we have discussed in last class, because maximum oxidizing capacity is possible for KMnO4 only if the medium is acidic. So that is why we take acidic medium. So FeCl2, that is actually present, because in presence of HCl, the iron 2 plus that will remain in these formats, and there is complete dissolution. That means all FeCl2 that is in it is in ionic form, Fe2 plus and Cl minus. Now the amount of iron present in the sample is Y%. That also we have to find. First you have to find the value of X, then you have to find the value of Y. Some more assumptions are also there, that is KMnO4 reacts only with Fe2 plus, because in the sample except Fe2 plus, what are the other substances present, that is the impurities may be present, that we have to don't take care of, because KMnO4 is reacting only with Fe2 plus. So this information, this assumption is already given. And molar mass of iron, that is, you can say the atomic mass of Fe, that is actually 56 gram per mole, because ultimately we have to find the percentage of iron, and then you will need this value. So how we will start? First of all, in the balanced equation, and how to balance the equation, that is the reaction between Fe2 plus and KMnO4 minus. I am just writing the ions. So how to balance it in detail we have already seen. I am not wasting time on that. So here 5 equivalent of iron 2 plus, that is 5 moles of Fe2 plus, basically that is equivalent to 1 mole of MnO4 minus. So this is the important relationship. How many moles of Fe2 plus is actually required for reaction with MnO4? So this is the ratio, 5:1. Now first this 20 that is 12.5 ml and 0.03. This calculation we will do. So when there is volume in ml and molarity, we directly multiply this and we get the corresponding millimoles. So when you multiply this, what you will get? You will get 0.375 millimoles of KMnO4, or you can write MnO. So this number of millimoles of MnO4 required when it is reacting with 25 ml solution. Now if it is 10 times high, because ultimately you have to find X value into 250 ml. So this is for 25. So if it is 250 ml, it should be 10 times extra. So now it will be 3.75 millimoles of MnO4 or MnO4 minus for 250 ml sample. So it is just 10 times extra. Now you have to remember, for each mole of MnO4 minus, the corresponding value moles for Fe2 plus, it is 5 times. So that is why if you want to get the number of millimoles of iron, you have to convert it, that is convert it to moles of Fe. For that you have to multiply with 5. So number of millimoles of Fe2 plus, that should be equal to 3.75 multiplied by 5, and this will give you 18.75 millimole. Now this is millimole. If you want to get moles, now it will be 18.75 multiplied by 10 to the power minus 3. Now ultimately you have to express it in this format, x into 10 to the power minus 2. So the same thing you can also write like this. Now look at it. It matches with this format as it is given. So x into 10 to the power minus 2. So this is the value of x. So the value of x is 1.875. So now we know the value of x. Next we have to find the value of y. That means the amount of iron present. Now once we know the number of moles of iron 2 plus, the rest of the work is very easy. So with this number of moles, that is the value of x, simply multiply 56, then you will get the mass. So mass of Fe2 plus divided by this 5.6, that will, and then you multiply it with 100, that will give you the value of y. So here first I will write the value of number of moles which we have just obtained, 1.875 multiplied by 10 to the power minus 2. So this is the number of moles. If you convert it to mass, then it should be multiplied by 56. So this is the mass of iron that is present in the sample, divided by given mass, then multiply with 100, so that you can get the percentage. So here the calculation is easy because 56 and 5.6, so it will be 10 to the power minus 1, then 10 to the power minus 2, these two will be cancelled. So ultimately you are getting 18.75%. So you don't need calculator, it's simple calculation. So the value, this is the value of y and this is the value of x. Okay, so this will be the answer. So now we will finish the other two titration. After the first one is permanganate titration. Now the second one is dichromate titration. So in dichromate titration, basically how this name we are getting, this name we are basically getting from the ion Cr2O7 2 minus. If you simply remove 2 potassium, you will get dichromate ion. So this is actually the oxidate, and here also the medium is acidic, and for creating acidic medium, basically we use dilute sulfuric acid solution. So here you can see in conical, you will take some reducing agent because here Cr2O755, that is actually oxidizing agent. So you need some reducing agent. So here we have this reducing agent along with some indicator. So that indicator actually produce this type of blue color once the reaction is finished. And dichromate we have taken in burette. You can see the color is orange or deep yellow because K2Cr2O7 when it is in solid form it is deep orange, and when you make solution it is basically depending on concentration it can vary from yellow to deep orange color. So that is why the solution in the burette in the picture that is in orange color. Okay, so here the principle of dichrometry. Just in a case of permanganate titration we use the term permanganometry. Metry means to measure, and as we are that is the titration name is dichromate, and we are measuring the concentration of the reducing agent, unknown concentration if you have taken, that is the analyte. Remember analyte. So that is why the name is dichrometry. So the principle of dichrometry is based on the fact that here this ion, that it is the oxidizing agent, that means it will be reduced by some reducing agent that we will take in this conical to chromium 3. So what is the oxidation state of chromium in Cr2O7 2 minus? So suppose the oxidation state is X. I am writing here X. So 2X because 2 chromium present plus 7 oxygen. That means for each oxygen it is minus 2. Total 7 oxygen. Overall charge is minus 2. So the value of X is 14 minus 2, 12 by 2. So it is basically 6. So here oxidation state of chromium is plus 6. And the fate of chromium, it will be converted to chromium 3 plus. So from plus 6 oxidation state, it is converted to 3 plus. So it is obviously reduction. Now, if you consider it as the half reaction, you can also balance it. We'll do so. So look at this reducing agent that you can use. So it can be reduced to chromium 3 plus ion, Cr3 plus, by some reducing agent, and normally the reducing agents that we take is Fe2 plus that you have already seen. In case of the previous titration, that is permanganate, we have used it already. We can use tin2 plus. So the fate of Fe2 plus we know it will be oxidized to Fe3 plus. When you take Sn2 plus, it will be oxidized to Sn4 plus. When you take I minus, it will be converted to I2, iodine, from I minus to iodine. So this is oxidation. Then you can also take oxalate. Oxalate ion you have already seen in the last class. That is how it reacts with MnO4 minus. So oxalate that will be converted to CO2. So here plus 3 oxidation state of carbon that will be converted to plus 4. So all these are basically different examples of reducing agent that you can combine with permanganate titration. Sorry, dichromate, dichromate. So here mostly the analyte that is taken in the conical, and potassium dichromate that we taking in the burette. Next, you also have to add some indicator. In case of KMnO4, we have not used any indicator because that there it is acting itself as the indicator, and there is some auto color change. Remember, in KMnO4 titration, when there is some extra 1 drop extra of KMnO4, then the solution turns pink, which proves that MnO4 minus it is present excess. So it is the end point, and then you stop the titration. But in case of Cr2O7, there is no such thing. So when Cr2O7 it is converted to chromium 3 plus, there is no such. That is, you have to use some indicator. Extra indicator you have to use, not like KMnO4. You will be able to understand the color change. And normally, what indicator we take? We take diphenylamine. So Cr2O7 2 minus, it oxidizes the indicator PH2NH. So this is a strong oxidizing agent, and in acidic medium, this indicator also, when it is oxidized by this, because we know indicators, they are actually they also remain in oxidized form and reduced form. So when it there is equivalence point achieved, that is the end point, then it produces this type of intense blue color. So when there is this type of color, you just stop the reaction. So that means now the reaction is over. So here, this is the indicator. Remember it, PH2NH, diphenylamine. Now this method, though here we have mentioned Fe2 plus Sn2 plus I minus, but mostly it is used for the estimation of ferrous salt. Ferrous salt means iron 2 plus. Fe3 plus is ferric, but Fe2 plus is ferrous and iodide. Mostly for estimation of these two. Estimation means suppose you do not know the concentration, you have taken a fixed volume of iron 2 plus solution or iodide solution in the conical, and then you are titrating with known concentration of potassium dichromate, and now we already know how to balance any redox reaction. So when you look at the balance reaction, you will be able to understand how many moles of iron will be reacting with how many moles of Cr2O7 2 minus. So once you know this mole ratio, and from this burette reading, you will be able to know what is the volume required for Cr2O7, concentration of Cr2O7 already known. Then the analyte, you do not know the concentration, you only know the volume. But as you know, the mole ratio of this any oxidizing that is any reducing agent that you are using, it may be Fe2 plus, it may be I minus. So depending on that, that is the mole ratio, you will be able to measure the concentration of Fe2 plus or I minus that is present in this solution. So suppose that you have taken 20 ml and the main, so in the 20 ml, how many moles are present? So in the from the main solution, suppose the main solution you have made 500 ml or 1 liter, then you will also be able to understand what is the number of moles present in 1 liter, and that is actually the molarity. Fine. So Cr2O7, its fate is it is converted to Cr3 plus. So here we will balance this half reaction. Cr2O7 2 minus converted to Cr3 plus. So the first thing that you have to see here, 2 chromium present in left hand side, only 1 in the right hand side. So I will put here 2. Next thing is you have 7 oxygen in the left hand side, but no oxygen in the right hand side. So that is why I will write here 7 water molecule. Remember, in this way we that is number of hydrogen and oxygen both side, you can make it same. So here I have written 7H2O, but when you have written 7H2O, there is 14 hydrogen present in the right hand side. To make up that, I will write here 14H plus. H plus you can write because it is acidic medium. Now hydrogen, oxygen both are balanced. Next thing that you have to notice, what is the charge? In the right hand side, total positive charge is 6 plus. In the left hand side, total positive charge 14 minus 2. That means 12. So to balance it, you have to write 16 electron. So chromium to Cr2O7 2 minus, when it is converted to chromium 3 plus, basically 6 electrons are required. So this is the balanced half reaction. This is the reduction reaction. Now whether you have taken Fe2 plus or I minus, the other reaction will vary. Fine. So this is the half reaction. Now when we will solve this problem, you will be able to understand that is the whole balanced equation, that you will be able to understand how we are getting there. So the question is saying that consider titration of potassium dichromate solution with acidified more salt. More salt is nothing but iron 2 plus. Number of moles of more salt required per mole of dichromate. So now more salt full formula, even if you do not remember, it is okay. Just see, more salt is containing Fe2 plus. Now in the previous slide, I have already written the half reaction, which is Cr2O7 2 minus 14H plus 6 electron, 2 chromium 3 plus, and 7 water molecule. Now I will write the other half reaction. The other half reaction is Fe2 plus converted to Fe3 plus. And here we have to write one electron, then both side charge will be equal. Now these two half reaction, if we want to balance, we have to multiply this equation with 6, right? Now what I will do, I will directly write here 6. Next step, you have to add these two equations. This electron will be cancelled, and the final balanced equation, basically see, if you here you have to select the option 3, 4, 5 or 6. Even without writing it, you can understand that the answer will be 6, because it is asking the number of moles of more salt required. So see, for 1 mole of K2Cr2O7 you require 6 moles of Fe, so that is actually the answer. But here I will write the full equation. 2 plus 14H plus, this side we have chromium 3 plus, 6 iron 3 plus, and 7 water molecule. So this is the final balanced equation, but this is ionic equation. If you mostly we deal with ionic equation in redox reaction chapter, but if you want to convert it to that is molecular equation, neutral molecular equation, that also you can do. So for that, what you have to do, you have to add 2 potassium plus, so that you can get K2Cr2O7. Then Fe2 plus, now in more salt it is basically iron sulfate. So what we will do, we will add 6 sulfate, H plus. Now H plus, it basically it is coming from H2SO4. Now 14H plus means what? 7 H2SO4. So you need 7 sulfate ions. Now come to the right hand side. In right hand side, chromium 3 plus, it actually remains as chromium sulfate salt. That means when there is 2 chromium, basically you need 3 sulfate. Then you have Fe3 plus. So it basically remains as ferric salt, which is Fe2SO4 whole 3. So per iron, that is for 2 iron you need 3 SO4. So there is 6 Fe. So that means you need 6. Sorry, it is Fe2SO4 whole 3. This is the formula. And here we have total 6 Fe3 plus. That means for 2 iron, the requirement is 3 SO4. So for 6, it should be 3 times. Basically, it is 9 SO4 sulfate ions. And water molecule, leave it as it is. Now the total sulfate, if we count, here we have 13 sulfate. This side we have 12 sulfate. That means 1 sulfate is less. Now see, 2 potassium you have added, but that is not present in the right hand side. So that is why I will write here K2SO. In ionic equation, you will not find all this because the spectator ions that will not be present. So the final molecular equation, it should be, how it should be? It should be K2Cr2O7 plus 6 FeSO4 plus 7 H2SO4. Then come to the right hand side, it should be Cr2SO4 whole 3. Then we will have 3 Fe2SO4 whole 3 and water molecule as it is. Now look at this. This is the final balanced molecular equation. K2Cr2O7, 6 FeSO4, 7 H2SO4, 1 K2SO4. Chromic sulfate, this is ferric sulfate, and water molecule. But this is, I am just showing you for extra information. To solve this problem, obviously the up to this part is enough to answer the question, which is 6. Fine. So this type of problem you can also get, suppose dichromate related problem. Instead of more salt, there may be any other reducing agent, such as it may be I minus, it may be SN2 plus, or it may be oxalate ion. Remember oxalate ion? Oxalate we get from oxalic acid. Oxalic acid is CO2H attached to another CO2H moiety. If you remove the 2 hydrogen, it will be CO2 minus, CO2 minus. Okay? So this type of problem, it may be with any other reducing agent also. So here, now you know how we have balanced these two half equation and how we are obtaining the final equation. So in the final equation, see, these two, the ratio is 1:6. So for each mole of dichromate, the requirement of Fe2 plus is 6 times high. So that is why you can write it like this. That 6 Fe2 plus, that is equivalent to 1 mole of Cr2O7 to 1. So this relationship is actually important when you will actually solve the problem. Next we have another problem. The mass of potassium dichromate crystals. Potassium dichromate crystals means crystals of this molecule that we have to find. You have to find mass required to oxidize 750 centimeter cc of 0.6 molar more salt. So again we are doing the titration between K2Cr2O7 and FeSO4, which is basically the iron Fe2 plus salt present in more salt. So K2Cr2O7 plus FeSO4. This is the reaction of it. Now how we will write, remember we have already seen that 6 Fe2 plus, that is actually equivalent to 1 mole of Cr2O7. Now you know the volume and molarity for the iron 2 plus, but you do not know what is the number of, that is a number of moles or millimoles of Cr2O7, but that you can easily calculate from this 1:6 ratio. So first multiply these two, 750 multiplied by 0.6. So when you multiply this, you get millimoles of Fe2 plus, right? Now here molar mass of more salt is given, but actually molar mass of more salt is not required. You need the molar mass of K2Cr2O7. But before going to, that is before doing the calculation of molar mass for K2Cr2O7, first we will see what is the number of millimoles for Cr2O7 that we require. So here 6 moles of Fe2 plus is required reacting with 1 mole of Cr2O7. So when it is 650, 0.6 millimoles, or you can also write 6 moles I have written, you can also write 6 millimoles. So here, this also will be 6. So this number of millimoles that will react with 1/6 of 750 into 0.6 millimoles of Cr2O7. And this value is, I'm writing 0.45, which is, if you multiply this you will get. So this is the number of, let me do the calculation once. So basically it will be past 450 divided by 6 millimoles, but if you convert it to moles, then it should be divided by 1000, and then it will be 0.45 divided by 6 moles of Cr2O7 or K2Cr2O7. Fine. Now we will calculate the molar mass of K2Cr2O7. So here we have 2 potassium. So 2 into 39 for potassium, 2 into 52 for chromium, 7 into 16 for oxygen. So you will see, you will get 294. That is the value for molar mass of K2Cr2O7. Now when you multiply with these 294, then you get, and that is actually option C. Okay, so it is simple. The mass of K2Cr2O7, that is actually the answer that we require. But from this relationship is important. So whatever number of millimoles you are getting, when you divide it by 6 and convert it from millimoles to moles, then you get the number of moles of K2Cr2O7. Because whatever is the number of moles of Fe2 plus, when you convert it to dichromate, it is always 1/6 times less. Okay, so that is why we have divided this value with 6. So answer is 22.05. Next problem. Again, iron 2 plus in acidic medium reacting with Cr2O7. So 15 ml aqueous solution of Fe2 plus in acidic medium. So 15 ml Fe2 plus in acidic medium, it is reacting with 20 ml 0.03 millimoles of Cr2O7 2 minus. Okay, now from the relationship, that is 6 Fe2 plus, that is equivalent to 1 milli. So here you can write that 1 mole Cr2O7 2 minus, that actually reacts with 6 moles of Fe2 plus. Now it is also true for millimoles. Both sides I am putting here millimoles. Now 20 into 0.03, 20 into 0.03, this number of moles of Cr2O7 that will react to it, it should be 6 times high. So this is the number of millimoles of Fe2 plus. Now millimoles of Fe2 plus, you do not know the molarity. Suppose the molarity is M. You only know the volume. But when you multiply volume with molarity, you get millimoles. So 15 into molarity, that is actually equal to 6 into 20 into 0.03 millimoles. So this is the millimoles of Fe2 plus, and that is equal to 15 multiplied by molarity, that we do not know, we have to calculate it. So capital M, you will get it 6, that is this whole calculation. So you will see, you will get it 0.24. But you have to express it, the molarity of Fe2 plus solution in this format, gap into 10 to the power minus 2. So 0.24, how you can write it? 24 into 10 to the power minus 2. So when you compare it with this format, this is the value of x. So this is the answer. Okay. So this relationship is enough. Just remember it. You don't have to balance each time when you solve any problem. So this is the relationship, and also this, remember this relation, mostly the problems you get related to Fe, but not necessarily it will be so. It may be oxalate also, it may be I minus also. So if you can't remember this relationship, then you have to balance it and you have to find what is the mole ratio of this oxidizing agent and the reducing agent. Once you know the mole ratio, rest of the part is easy. Okay. Next we will start the third titration, which is Iodimetric and iodometric. Now you can see here two terms. So there is difference in spelling, iod and iodo. But whatever it is, we will use either I2 or we will use I minus. Okay. Now in this titration, an iodine solution is reacted with reducing agent. Now when you add some reducing agent with iodine, what happens? It reduces I2 to I minus, because here it is having oxidation number 0, and after reaction you are getting oxidation number -1. So obviously it has accepted electron from the reducing agent. Here the indicator that we use, touch. Now why we use indicator? Come to this picture. First of all, you have to know that iodine, if you directly take in water, it is not soluble. When you add some Ki, it forms Ki3 type of complex, and now it is soluble in water. So direct iodine we cannot make solutions. It is always associated with some Ki. So that is why it is written in this way. So suppose here we have we are adding some iodine dropwise. So that is why now the solution is yellowish or brown. Now, if that is positive taste, that means when you are adding starch to it, then it will be converted to this type of blue or deep purple color solution. So what happens? Starch, it forms some complex with iodine. So from this color, you can say that yes, iodine is present. So whenever you are adding some starch to any solution, if there is presence of iodine, it will change its color to blue. But suppose there is no iodine present, then this type of blue color you will not get. Fine. So that is why take any sample. If you want to know whether there is iodine, free iodine, obviously free iodine present or not. If we want to know free iodine present or not, we just add that is starch, and free iodine, it forms some complex with starch. Then it forms this type of blue color complex. And if free iodine is not present, there will be no blue color, and the color is very intense. Even if very minute amount of iodine is present, then also you can easily observe the blue color. So no blue color means there is no iodine. So in this way, this indicator will help us. So suppose you are doing this titration, you have taken some iodine solution and you have added reducing agent, and you have also added the indicator. So initially, before the reaction, when you are adding the starch indicator, what will happen? Initially the color will be blue. As soon as the reaction is progressing, the reducing agent will convert all the free iodine to I minus. Now once the reaction is complete, there is no free iodine present. That means now the free iodine cannot form complex with the starch indicator, so there will be no blue color. So when the blue color is vanished, it proves that reaction is complete. Fine. Similarly, the reverse also we can do. Suppose you have taken I minus solution and now you are added some oxidizing agent, and it will convert I minus to iodine. Now initially when you will add starch indicator to this solution, there will be no blue color, but as soon as the reaction will progress, there will be generation of blue color. But remember, obviously it will not be able to indicate the end point, because once the first iodine is formed, then also it is blue color. Once all the I minus is converted, then also it is blue color. So mostly it is used for the first case where you have taken some free iodine and it is reacting with some reducing agent. Once the reaction is complete, all the iodine consumed, that means no blue color will be there, and that is the indication that the reaction is complete. Now what is the difference between IOD and iodo? So iodometric is basically indirect, but when it is iodimetric, it is direct method. But remember, mostly the application of this method is comparatively high than the direct method. But we will see both of them. Direct titration, basically the direct titration, that is iodimetric, that is comparatively simpler. So how it is simple? Here we take reducing analyte. So remember this part that I have written here, that I am writing it again. So in this case, analyte is reducing agent. That means the concentration of Ra, whatever reducing agent you have taken, concentration of it you do not know. You know the concentration of iodine. And now it is converted to I minus. So once the reaction is over, what is the amount of iodine required, and from the mole ratio of iodine and reducing agent, you will be able to understand what is the concentration of the analyte. That is the unknown concentration of the any reducing agent that you have taken. And here only one reaction is involved. Direct we are doing the titration. And standard solution of iodine. Standard solution means the solution for which you know the concentration. So you are using some standard solution of I2. So it means you know the concentration of this iodine solution. This is iodimetric. Now what about iodometric? So when it is iodometric, so in this case, now the analyte is oxidizing agent and two reactions are involved. Standard solution sodium thiosulfate. Now what it means? See, so first what we do, we take I minus, that is any iodide, and this iodide it reacts with some oxidizing agent. So this oxidizing agent is basically the analyte for which you are trying to calculate the concentration. You do not know the concentration. Now I minus will be converted to iodine. Basically you also do not know what is the concentration of I minus as well as OA, that is the oxidizing agent. So this is the first reaction that you have to do. Now the iodine that is produced in this reaction, this iodine, now you will treat it with sodium thiosulfate, Na2H2O3. Now Na2H2O3 is basically reducing agent, where this H2O3 2 minus ion itself will be converted to sulfate, and I2 will be converted to I minus. So see here we have done the second times another reaction, and this solution is basically standard solution. That means you know what is the concentration of Na2H2O3. Now from the, if you balance this equation from the mole ratio, basically it is simple, Na2H2O3 SO4 2 minus, and in this case it will be NaI will be produced. NaI is nothing but I minus. So from the mole ratio of these two, you will be able to calculate what is the number of moles of iodine. Once you know the number of moles of iodine, that is obviously coming from the first reaction. Now from the mole ratio of this iodine and oxidizing agent, indirectly you can also calculate what is the number of moles involved for this oxidizing agent. So that is why we are saying that this is not direct titration, this is indirect titration, where you are doing the reaction two times. So you have started it with some iodide solution and any oxidizing agent. So the important difference is you need some oxidizing agent, not just any oxidizing agent. It should be such that it can oxidize I minus. Okay, so that criteria must be fulfilled, because if I minus is not converted to iodine, second reaction is not possible. So that is why first this oxidizing agent is oxidizing iodide to iodine, and this iodine you are reacting with the standard solution of sodium thiosulfate, and from the mole ratio of these two, now you know the number of moles of iodine. Once you know the number of moles of iodine from the first reaction, that is once it is balanced, you will know the mole ratio of this oxidizing agent and iodine. Finally you can calculate number of moles of this oxidizing agent. So this is the difference. So first we will see iodometric titration. Here quantitative oxidation of some reducing agent So here, which reducing agent we have taken? We have taken arsenious acid, H3ASO3, and in presence of iodine, here iodine is basically acting as oxidizing agent, and this is reducing agent. So see here, which ion is involved? ASO3, 3 negative. If you remove 3 hydrogen, it is ASO3, 3 negative, and this side it is ASO4, 3 negative. Here oxidation number, if you do the calculation, you will see it is +3. Here it is +3. So from +3, as it is reducing agent, it has lost electron. So this is basically oxidation. This is basically reduction. So here we are using standard solution of iodine. So iodine standard solution, any reducing agent. Here for example, we have taken arsenious acid. Now as I have already said that free iodine, it is insoluble in water. So we add some Ki. So it remains as Ki3. But whatever is the amount of Ki3, it is directly equivalent to iodine. That is 1 mole of iodine is generating 1 mole of Ki3. So whatever is the number of moles of Ki3, that is directly equal to the number of moles of iodine. That it is simple. So in this case, starch is used as an indicator for detecting the presence of iodine, as it forms intense blue colored complex with iodine. And once all the iodine has been used up, the dark color it will be fading away gradually. So once the reaction is over, you have only I minus. So blue color formation is not possible. Okay. Now when this type of equation is given, you can, and suppose if you have to balance it, just break it into half reaction, or the other, there is another method also, whatever you find suitable, you can balance it. But as I have mentioned, mostly that is the application of iodometric titration is comparatively more than this one, that is Iodimetric. Next one is Iodometric. Now the use of this method, it is limited only for the reagents which has the capacity to oxidize iodine. So not just any oxidizing agent, it should be such that can oxidize I minus. And here we have 2 examples, copper 2 plus chlorine. So when copper 2 plus is oxidizing I minus, the fate of copper 2 plus, it will be converted to simply metallic copper. When chlorine is the oxidizing agent, its fate will be converted to chloride. Fine. So in this case, an equivalent amount of iodine will be first liberated. When the given sample of an oxidizing agent, it is oxidizing potassium iodide in an acidic medium. Now, normally, I will discuss this later also. Though here it is written acidic medium, but remember this iodometric or iodometric titration, it is not done in very strong acidic medium or very strong basic medium. Mostly it is kept, it is close to neutral. So it is written here acidic, but it is not strongly acidic. It is close to neutral or maximum pH 8. It should not cross that. So strong basic medium, strong acidic medium, both we have to avoid. And why it is so, that also I will discuss. Just remember, strong acidic, strong basic, both are detrimental for titration, that is iodometric or iodimetric. So here we have taken this example where copper 2 plus is the oxidizing agent and I minus, that is the reducing agent. So copper 2 plus, sorry, it is not copper, it is copper plus. It is converted to copper plus. So this reaction is actually reduction, and I minus is converted to iodine. So this is basically oxidation. Fine. Now the iodine that is produced here, this is the first reaction. This iodine, that is the equivalent amount of iodine generated. So you can see this is balanced equation. For 2 moles of copper, there is liberation of 1 mole of iodine. So this is the mole ratio. Now in the second equation you can see equivalent amount of iodine that is generated in the above reaction. Now it can be titrated using standard sodium thiosulfate solution. So this is standard and this is reducing agent. Now this is the oxidizing agent and it is converted to Na2S4O6. Fine. So in S4, sorry, one mistake I have done in the previous slide. So here, sorry, it is not SO4, it is S4O6 okay. So Na2S2O3, now it is converted to Na2S4O6 and here NaI. So this part is basically reduction and this part is basically oxidation. So Na2S2O3, that is the reducing agent. It is a standard solution we are using. That means we know its concentration and it is again converted to iodide. Now in the second reaction you can use the starch indicator, because once all the free iodine is consumed, the blue color will be vanished, which is indicating the end point. Fine. This is the second equation. So remember, this note is important. The titration usually performed in neutral or mildly alkaline or weakly acidic. So either it is weakly alkaline or weakly acidic, but strong, that is very low pH or very high pH, that should be avoided. Right? Now we will compare once more. So iodimetry, remember, total two reactions. This is indirect and this is direct. So in iodimetric titration, an iodine solution is directly titrated with reducing agent or solution. But in iodometric, the iodine which has been produced as a result of previous redox reaction, now that is treated with some reducing agent, which is mainly Na2S2O3. And iodometric, it is indirect, this is direct. Two reactions are involved total. Here only one redox reaction. In iodometry, iodine gets oxidized first and then reduced by some reducing agent, and here in iodimetry, it is one-time reaction, iodine only gets reduced. So in this way, we can compare. Now, we will see why strong acidic medium or strong basic medium we should avoid. So suppose if it is very strong medium, the first problem that arises is that starch, which we use as indicator, there is a tendency to hydrolyze and it is converted. Starch is actually very complex molecule. Several glucose units are linked together. So when there is hydrolysis, the starch will be decomposed. It will be hydrolyzed to that is glucose unit. So that is why strong acidic medium, it is harmful for the indicator, and not just indicator. It is also harmful for the I- solution. So in strong acidic medium, what happens? That as you are doing the reaction, there is obviously atmospheric oxygen present. Now this atmospheric oxygen, so it is iodide. Oxidation of iodide can occur. So whether it is iodometric or iodometric, I- is involved, right? So this I-, there is a tendency, it reacts with oxygen and it is converted to iodine. That means oxygen itself is acting as oxidizing agent, but this reaction is possible only if pH is very low, that is if you are using strong acidic medium. So in strong acidic medium, you have two types of problem you have to face. This one, that is the problem you are seeing here, and the second problem is indicator problem. The starch indicator, it will be decomposed. Now what about the basic medium? In basic medium also, there is a chance of disproportionation. So in basic medium, the problem is actually with iodine. So iodine here, in presence of hydroxide ion, it is converted to I- and iodide. This is iodide, not iodide, DITE. And this iodide, this is the first equation. Look at the second equation. This iodide, now it is also converted to iodate, an I minus. So whether you consider IO minus or 3IO minus, in both cases, iodine is basically oxidized. See, if I write the oxidation number, IO minus, here oxidation state of iodine is basically +1, because overall charge is -1. For oxygen it is -2. So obviously iodine will be plus. And for iodate, IO3 -1 charge. So here oxidation state is +5. Now basically what happens, iodine, it is converted to I -1 as well as it is +1. And if you consider this reaction, it is -1 and +5. So this is basically disproportionation, because iodine, it is oxidation state 0. It is converted to +5, loss of electron, and -1. Even if you consider IO minus, then also it is +1. So whether it is +5, +1, it is basically disproportionation, because this is reduction and this is oxidation. So +5 I have written for iodate, +1 I have written for iodide. So these type of reactions occur. Now these two reactions you can also directly write it in the form of IO3. So see here, for the second reaction, 3IO minus. So if I multiply this equation with 3, it will be 3 iodine, 3 HO, 3 HI, 3 IO minus. Now I am writing the other equation without multiplying anything. So this part is cancelled. Now as a whole, what you are getting? 3 iodine, 3 HO minus, 3 HI, IO3 minus, 2 iodide. Now what I will do, if you add both sides, 3 HO minus, so this part you can write it as if it is 3 water molecule, because HI, it is H plus and I minus if you consider in this way. So it is 3 water molecule and 3 I minus. So what I am doing, so the purpose of doing this is, now this equation you can write in this way: 3 iodine, 6 HO minus in the right hand side, IO3 minus, 2I, 3I, and water. So basically I am doing both the reactions, so that, because sometimes in problem it is mentioned as that iodine is disproportionate to I minus, that is -1 oxidation state, and it is converted to iodide with oxidation number +1. Sometimes it is mentioned that it is disproportionate to iodate, which is IO3 minus. So both are actually true. See, if you break the equation, it will be like this. First there is formation of IO minus, then this IO minus finally converted to IO3. So what I have done, I have combined these two equations. Now you can see, from zero oxidation state in presence of strong basic medium, it is converted to +5 and -1. So this is basically oxidation, and this part is basically reduction. So in this equation, it is basically disproportionation to +5 and -1, but it may be also disproportionation to +1 and -1. Both are possible. Fine, both I have shown, so that when you get problem, there is no confusion. Now related to this, if we solve this problem, the idea will be more clear. Iodometric titrations are usually performed in neutral or mildly alkaline or weakly acidic solution. Which of the following statement is not valid for this observation? Which statement is not valid, I mean not related, or it is not true? The first statement is saying in strong alkaline medium, iodine disproportionate to I minus and IO1. So this is basically true, that we have just seen. Then in strong acidic solution, starch used to detect the end point that is indicator, the purpose of using it to detect the endpoint, but it itself hydrolyze or decompose. That I have also mentioned. This is the problem in strong acidic medium. This is also true. The third statement is I minus produced during titration tends to be oxidized by the dissolved oxygen in acidic medium. This is also true. Remember, in strong acidic medium, it is talking about this reaction. So this is also true. Now the last statement, this is actually not related, and this is actually the correct option. So it is saying that reducing power of the reducing agent that we use in Iodimetric. Remember, Iodimetric, there is only one reaction involved. It's converted to iodine. Reducing agent, its reducing power is increased in strong acidic medium. But this general statement you cannot make. This type of general statement you cannot make because that may depend on what type of reducing agent you have taken. This statement cannot be true that in strong acidic medium the reducing power of any reducing agent is always increased. No, this is not at all possible. Basically, this statement itself is wrong. Even if you do not consider iodometric titration, the statement itself is wrong. Okay, so this is the statement which is not valid for this observation. These three reasons are actually the reasons for which we should do this titration, not in weakly alkaline or weakly acidic, but not strong acidic or basic. The first three statements are actually the reason, not the fourth one. The fourth one is not the reason. So we are at the end of the session. One more problem also we will discuss, which is also related to iodometry or iodometry, and then this part, that is redox reaction as the basis of titration, that part will be complete. Another topic will be started. Thank you for listening.